So in example 5, we have an exponential distribution. It doesn't tell us what the mean is this time. I guess we'll just have to call it beta. And d and m are some constants, so very little concrete in this problem. We have to prove this strange expression. It says, oh, I see here we have conditional probability. This line is conditional probability. So we'll have to remember that, the formula for conditional probability. We have to prove that the probability of y being bigger than d plus m, given that y is bigger than d, is equal to the probability of y being bigger than m. And somehow that's supposed to have something to do with the word memoryless. The exponential distribution is known as the memoryless distribution, and so we need to interpret that and justify it somehow. So the first thing I'm going to do with this problem is remind you of a formula that we derived back in example 2. So if you haven't watched example 2 in the recent past, you should go back and watch that right now, because we're going to be using a formula for the exponential distribution. It tells us that the probability that y is bigger than c is equal to e to the negative c over beta. That's going to be very useful. We calculated an integral back in example 2 to find that, but we're not going to recalculate it now. I'm just going to use it. So I'm going to go ahead and start working out the left-hand side of this expression. It might get a little complicated, but hopefully I can simplify it down to the right-hand side. So the left-hand side, LHS, is, well, remember, we have to use conditional probability here. The probability of A given B, this is an old formula. I gave a lecture video on it many moons ago. So if you don't remember that, you can always look up my previous lecture on it. It's right here on Educator.com. It's the probability of A and B, or A intersect B if you want to use symbols for it, divided by the probability of B. So let's figure out what that means in this situation. It's the probability that y is bigger than d plus m and y is bigger than d, divided by the probability of y being bigger than d. Now, let's think about that. If y is bigger than d plus m, then y is definitely bigger than d. I didn't say it here, but I'm assuming that d and m are all positive numbers. D and m are positive numbers. So if y is bigger than d plus m, then it's definitely bigger than d. So I don't really need to say y is still bigger than d. I can just say the probability that y is bigger than d plus m. And I don't need to emphasize at that point that y is still bigger than d, because it's automatic, divided by the probability that y, and I don't know why I said y plus d above, it should have been a bigger than. Y is still bigger than d. So we can calculate each one of those, and we're going to use this result from example 2. So we'll use this result right here from example 2. That's e to the negative. Now our c here is d plus m, so d plus m divided by beta, all divided by e to the negative d over beta. So we have a fraction of exponents here. We can do a little flipty-flipty and maybe flip it up to the top there. So that's e to the positive d over beta, since we pulled it out of the denominator, minus d plus m over beta. And now that simplifies down a little bit into, well, the d over beta is cancel, and we're just left with e to the negative m over beta. And again, if we use this result from example 2, that's exactly, whoops, that 2 sure looks like a 1, doesn't it? Let me change it into a real honest 2. So this is the probability that y is bigger than m. And lo and behold, we have the right-hand side appearing here. So we have proved our equation that we set out to prove here. I haven't really given much of an interpretation as to what that might mean, but I certainly know it's true. I certainly know that this equation is true, and now I have to think about what it really means. Let's say that, remember, the exponential distribution, what it measures is the waiting time until some random event occurs. Now, an example I used earlier on was some unpredictable event. Sometimes it happens and you never really know when it's going to happen. So the example I picked was your car being stolen. So let's have y be the waiting time until, how long do you have to wait just leaving your car around on the street until your car is stolen? So what does this equation mean? Let me pick values for d and m. So let's say d is 1 day, and m is 1 month. And then d plus m would be 1 month and 1 day. That's why I picked d and m in the first place, was because I was thinking ahead to this. What this is really saying, the probability, we have conditional probability here. This means, given that y is bigger than d, so suppose y is bigger than d, that means you made it through the first day without your car being stolen. So suppose your car is not stolen today. Isn't stolen today. That means you made it through the first day. Thank goodness. Y is bigger than d. So you made it through at least one day without any theft of your car. Given that you made it through today, what's your chance of making it through a whole month more after today? So then your chance of surviving, and surviving meaning your car is not stolen, not serving, surviving another month, an extra month on top of today. So what we're really calculating there is the probability that your car will now survive a day and another whole month, given that it's already survived 1 day. What we're saying here is that it's equal to, is the same as the chance of surviving a month from today, just starting today, as the same as the chance of surviving a month today. I keep trying to misspell surviving. Maybe I should find a different word. Surviving a month today. So the chance of surviving a month today is the probability of y being bigger than m. What that means, let's think about that. It means, well, you can think at the beginning of today, what's my chance of surviving a month? And you can calculate that out. It's the probability of y being bigger than m. And then maybe at the end of the day, you get through that day and you say, what's my chance of surviving another month? Well, it's the same as your chance was this morning of surviving a month from this morning. In other words, if you survive today, you get a fresh start tomorrow. So you get a fresh start tomorrow if you survive today. Hey, it means you just got lucky today. You get a fresh start tomorrow. Your probabilities of surviving another month don't change tomorrow. So it's not like the bad luck will build up. If you survive today, it doesn't mean you're more likely to have your car stolen tomorrow. It just means you got lucky and you get a fresh start tomorrow. Maybe you'll keep getting lucky. Your probabilities will keep staying the same. That's what it means to be a memoryless distribution. The exponential distribution is memoryless. At the end of today, it doesn't remember that you survived one day. It just restarts and it calculates anew for the next month. The exponential distribution is memoryless. It doesn't remember that you made it through today. It doesn't remember that you made it through today and sort of hold it against you and make you more likely to have a car theft tomorrow or the next month. It just says, hey, you got a fresh start today. I will compute the probabilities for the next month just the same as if we had started today, this morning, and calculated the probabilities for a month. I don't remember that you got through today unscathed. I won't hold it against you. I won't build up the bad luck. I will just count that. We'll count anew starting tomorrow. So that's what it means to be memoryless. So let me show you again how we did these calculations here. At first, I just treated this as an equation. I didn't try to think about what it meant. So I calculated this probability as a conditional probability, and I used my old conditional probability formula. If you don't remember the conditional probability formula, we got a bunch of problems on that in an earlier video here. It was near the beginning of this probability lecture series, so kind of scroll up to the top and you'll see conditional probability. And so I've got this conditional probability. I say it's the probability of one event and another event divided by the second event. But these particular events, one sort of subsumes the other. One absorbs the other. Because if y is bigger than d plus m, y is automatically bigger than d. So I don't need to write that y is bigger than d. I can just drop it out. It just disappears. And I can just include it in the fact that y is bigger than d plus m. And now each of these probabilities are in a format that is amenable to this formula that I used in example 2, that I actually proved in example 2. We did an integral back in example 2. So if you don't remember example 2, just go back and look. You'll see this formula. Same video as this one. Just scroll up and you'll see it. Probability that y is bigger than c is e to the negative c over beta. So I dropped those values of c, d plus m, and d in here. Did a little algebra to simplify, and I got e to the negative m over beta. So that was example 2 right there to get to there. And then I used example 2 backwards to go from e to the negative m over beta back to the probability of y being bigger than m. And then I noticed, oh, look, that's the right-hand side of my equation. So I'm done. I've proved that that equation is true. So it's one thing to prove that the equation is true. It's another thing to interpret it and really understand what it means. So I said, let's interpret this as a waiting time until something happens, in this case, until your car is stolen. So this is saying that if y is bigger than d, that means your car is not stolen today because you're waiting more than one day for it to be stolen. What's your chance of surviving an additional month after today? So here's that additional month. That d plus m is the additional month given that you made it through today. Okay. What we worked out is that probability is the same as if we had calculated this morning, if we had come in this morning and calculated what's my probability of lasting 1 month from today. So if we come in this morning and we say, what's my probability of lasting 1 month? We calculate a certain number. Or if we wait until tonight and say, well, I made it through one day, okay, what's my probability of lasting another month after this? We would have gotten the same number either way because those two numbers are equal. So if we can make it through today, on the condition that we make it through today, we will get a fresh start tomorrow. It'll still be exactly the same probability of lasting through another month. And that's why the exponential distribution is called memoryless. It doesn't remember that you got lucky for one day. It just restarts and starts calculating the same probabilities this evening that it calculated this morning. So you kind of get a fresh start, assuming you're lucky enough to survive through today. So that wraps up our examples on gamma distribution and exponential and chi-square distribution. Remember that the gamma distribution is sort of the overall family, and then two special cases within the gamma distribution are the exponential distribution and the chi-square distribution. Probably the most common of all of those in probability is the exponential distribution, and after that you'll be using the chi-square distribution if you take a lot more statistics. That's where chi-square distribution comes up. So that's the end of our gamma distribution lecture. Next up, we have a nice lecture on the beta distribution as we keep moving through our continuous distributions. This is all part of a larger lecture series on probability here on Educator.com. I am your host, Will Murray. Thanks very much for joining me today. Bye-bye.